Hello and good evening, everyone. Welcome to the fourth talk for Global Game Jam Singapore 2024, organized by Kueh 22. The talk is Game Server Architecture by Mr. Xiang Shen, the Chief Technology Officer at Century Games. So our speaker is a game industry veteran and pioneer. Previously, he co-founded his company Outact, an independent game studio in 2014, which is now a studio of Century Games. Prior to that, he was also the technical director at ROBLOX, where he led the multiplayer engine development, fueling ROBLOX's massive success, and was also a server team lead at Tencent Boston, where he managed game server development and operations. He was also previously working at EA and Ubisoft on numerous AAA titles as a software engineer. Xiang holds a Master of Liberal Arts in Management from Harvard University, a Master of Science in Software Engineering from Carnegie Mellon University, and Bachelor of Science in Software Engineering from Nanjing University. So tonight's talk is an introduction to game server architecture of different game types, from MMOs to social games. Xiang, you may begin when you're ready.
Okay, nice to meet you. Thanks for the intro. I will start sharing my screen. Give me a second. All right. Good evening, everyone. I hope we're on the same time zone. So yeah, today I'm going to give you a very quick overview of game server architecture. So before I start, just to give you a quick overview of our company, so you know that's why I'm here, why I was invited. So Century Games is founded in 2010. Now we have currently 1,500 employees worldwide, and we are so far a top 20 mobile game developer by global revenue. Some of the top grossing games we have, including Whiteout Survival and a full bunch of that. Whiteout Survival we launched last year. Currently, it is a top 1 grossing strategy mobile game. So we have a lot of mobile game server experiences. That's why I think it could potentially be beneficial if I can share it with you, so you will get an understanding of that. So because I do not know your background, so I wanted to start from the very basics. I'll take it very quick, so everyone will be on the same page. So I wrote here, it's definitely an incomplete definition of game server. It's I actually tried to use ChatGPT to help me. I couldn't find a really good description that summarizes what game servers do in a very short form. So far, I figured this might be good. It's basically a combination of software and hardware that hosts multiplayer game sessions, ensuring synchronized and stable gameplay for all connected players. I kind of feel this actually represents most of the game server's functionalities. And there are a few attributes which I think are very unique and important for game server. First is data persistence. Basically, you connect to the game server, you want to get your game progression stored over there, right? So next time you connect to it, you don't start over. So this is actually the key part of why we want the game server to be centralized in most cases, right? Because you don't want to store your game data on someone else's computer, right, or devices. And this means most of the game server architecture will include a data storage system, like whether it's a MySQL or NoSQL. Typically, it's part of the server architecture. The second attribute is very important is synchronization. We want to make sure all the data across all the users are perfectly synchronized. You don't want to make one change of your character and other players don't see it, or you are in a desync mode that you believe this is the right condition or this is the right number, but the other player believes the other way. So we wanted to make sure everything, all the data across all players are perfectly synchronized. And this is also very important because typically when we are dealing with massive multiplayer games, we are dealing with desync issues. We're dealing with data losses. And this is something we need to make sure the server architecture can help us to solve. And the next one is stability. And this is very obvious, right? We don't want you launch a game and server crashed and nobody else could play. And this is normally in connection with the next one, which is scalability. Because sometimes when you see a game launched, very successful, went viral, but all of a sudden the server is down and you just couldn't play the game. Most of the reason because of that is scalability. They just couldn't handle that much of the traffic influx. And a good example is Pokemon Go, right? When the game launched, I forgot which year it launched. I think for the first week, you literally couldn't play the game. And most of the time, the server was just down because so much request. And they eventually figured it out, scale up the server. And we saw this happen to a lot of other popular game launches. Even sometimes they got it fully prepared. Still, you just couldn't have a really good estimation on the virality. And sometimes you just need to make sure the server architecture is well prepared for that situation. The next one is security. Apparently, you store your data on the server side. You don't want the data to be breached by others, or you don't want the data to be destroyed in some way. You want it to be just securely stored on the server side, and only you could access to that. And for this purpose, you want to design the server architecture in a way that it preserves the security of user data. The other thing is like you don't want the server to be, as I just mentioned, breached by hackers or sometimes players. Players could, for example, they could forge network packages. They wanted to just say, okay, I gain 100 experiences, but actually they didn't. We need to have a mechanism to deal with these situations. We don't want the player to exploit the server loophole. So this is also part of the server security we need to deal with when we are designing the server architecture. The last one, but it's definitely not least, is performance, right? So there are actually two folds of this. First is the server response time. Right? You don't want to just send the request to the server and expect like a few seconds before the server tells you, okay, go. Right? You want the server to instant tell you, okay, go ahead. Or when you play a multiplayer game, like when you do one action, when you kill an enemy or loot a loot box, and you want an immediate feedback, right? You don't want to wait an indefinite time until you see the result. This is like part of the performance, I would say, it's server response time. I want to make sure like when the packet arrived the server side, it got the fastest possible route to process and return back to the player. The other part of this performance issue is when you are dealing with a large number of users, each user request is somehow a cost on your server side, and you don't want to just spend a lot of server resources just dealing with a small number of players. This a very good example is your server. You normally have a very powerful CPU, but if you do not design the server architecture well, sometimes you just waste your CPU time on I/O, which is like, for example, database query or even just a file query, network connection, right? Because these are all I/O. So you don't want it to kind of use I/O to consume, because when you are dealing with these kind of asynchronous protocol calls, the CPU is just waiting over there. You wanted to make it as efficient as possible. So you wanted to kind of mitigate these kind of I/O calls. This is also part of the performance we need to deal with. We want to make sure like we don't spend too much resource on just a small number of players. Okay, so this is basically what in my opinion, a definition of game server and all the problems we need to solve. So next, let me just start with the game server involvement, which I think is really important for you to understand why we are here today. In the very early days, that when we are talking about a game server, we talk about a simple client server, single server structure. And you can see all these, like, you can see my mouse, right? All these nodes are clients, right? They are connecting to the server, and the server just handle all their requests, and that's it, right? It's early day server structure. But here, the problem comes, right? Like, if there are more of the players, what do we do, right? A very simple implementation is just to call a multi-server structure. Then, okay, for this server, just we handle, say, 1,000 players. If there are already 1,000 players connecting to this server, we just spawn another server. So we handle another 1,000 players. This is basically a very typical multi-server structure. But apparently this is very cumbersome, and you need to remember which server you are in. Normally we'll use like IP, or use server ID, or the server domain, subdomain name. That was very early days, and you're definitely not dealing with these today. But it is how we were dealing with like a multi-server. So it comes a lot of problem, and another problem is, how do we share data across all the servers, right? Because all these servers are just standalone servers. All the data storage are just within this physical server. And there is no way to share these data across multiple servers. So all these problems just kind of get the server development evolved to this structure, which is tiered structure. So you can see here there is a gate, which is a gateway. So gateway is basically taking all the connections from the game clients. And then it will distribute these connections to dedicated servers. For example, these two players, because they are always playing this server, so the gateway will basically route them to this server. And then all the requests going forward will be redirected to this server. And so the players do not need to remember which server I've been playing, because the game gateway is doing the job for them. So they only need to know, okay, I connect to this game and I'm playing. And they actually are playing one of the server shards, which is actually, normally these are just a physical server, right? And then I mentioned earlier, how do we share data across servers? Then we just use a centralized database system to share data across them, right? So this is actually a pretty typical structure. It lasts for years, and it's even some of the games are still using this kind of structures. We call it like those single server. It's different from this kind of single server structure. Like nowadays, when we say single server structure, is typically about, we'll talk about this tiered structure. Like this dedicated server is still handling all the player requests and doing all the game logic, right? And doing all the player interactions, everything just within that. And they persist the player data or some of the game state data to the database behind. So a lot of game logic is still running within the server, like most of them are in the server memory. So this is actually a improvement over the multi-server structure. Oh, sorry, a little bit too fast. So, but the problem is, as I mentioned just now, the server actually handle all the game logic, right? So there is apparently a problem is when the game logic or the game features become overly complex. Say a MMORPG game. When you basically need to deal with terrain system, like 3D terrain, right? And you need to deal with path finding, and you need to deal with all the AIs. They are actually extremely expensive in terms of CPU resources. And then let's say normally a MMORPG server, we want it to be able to hold a couple thousand concurrent users. And in this circumstance, that server needs to be extremely large. I mean, in terms of capacity and performance. And normally it's kind of very tricky to do that. Apparently nowadays, if you use a cloud service, they will be able to give you a server with, say, 128 cores, like 1 gig of memory. It's totally doable. But do you really need that? Like, you could spawn this large server, but potentially most of the time you are not really using the server resource. So the CPU could potentially be running most of the time at about like single digit, and you are wasting a lot of computing powers over there, right? But you do need that, especially when the game has those events that has a big increase of traffic, spike of traffic. You want the server to be able to hold that. So in this case, if this is still a single server, you just put everything in one single server, you just need to face a extreme costly kind of situation. And how do we solve that? And this is the next structure, which is server clusters. You basically just offload a lot of the services I mentioned earlier, like the terrain service, pathfinding service, right? AI service, chat service, to a dedicated, nowadays we call that microservices. Early days we don't even call that, but nowadays we just say server components. But nowadays just microservices, right? You just create these microservices. Some of these microservices, they are stateless. By stateless, I mean, say like this, they don't actually persist at any of the data. They're basically just a computing unit. As I mentioned earlier, pathfinding could be purely stateless. All you need to do is you tell this server, okay, I want to start from point A and I want to end with point B, and just give me the most optimal path. And because this server already have all the terrain information, all those computing libraries, so they basically just return the optimal path to you, and you basically just take this. So you basically offload the path finding to this stateless server. And sometimes the server could be also stateful. For example, it could be just a chat server, right? You still want the player to be chatting with each other, so you actually keep some of the chat history, things like that. So that could be also stateful. But they could also be offloaded from the core game server. So by doing this, you offload a lot of game features, functionalities to different services, and then eventually they allow you to optimize the size of the actual game server. So the game server just needs to handle the typical game logics, and then you will be able to just scale them and without a huge cost. So this is a very common used MMORPG server structure nowadays, this graph. Apparently this is a very optimal, a very simple diagram, and you would expect the server to be much more complex, but it serves the purpose for this presentation. And then when we are dealing with different game genres, we actually we need to design different type of game servers, because it's never going to be like one server architecture fits all kind of scenario. It's just like what I was having trouble finding the right definition of game server, because they actually have includes a lot of different issues. So normally what we do is, for different game genre, we design different server architectures, and sometimes it's just with mixed structures. I'll give you a few examples later of this presentation. So this is roughly the server involvement. And then the next part, I want to give you a very quick overview of my server experience. The reason I want to give it this to you, because I've been in the game industry for 20 years. I feel like my experiences pretty much matches the server evolution. And it gives you a really good kind of recap of what I just told you. So let me just start with my first networked project, which is a personal project when I was, I think when I was in high school. So that was in like I think 1996 or 1997. I forgot. Sorry, I think late 1990s. Do you know MUD? MUD is multi-user dungeon. This is literally the first form of kind of a multiplayer game, the initial form multiplayer game. It's all text based. It was extremely popular in early internet days, and my personal project was like I developed a web-based mud game and with some kind of graphics. This is like I remember I used a technology called ASP. It's an active server page. So very old kind of tech stack. I remember it was using VB script. I don't think anyone uses that today, but it was one of the very few available server systems I could use. For that one, it's actually still a single server structure. I basically just put everything, all the game logic in one server. Literally just I kind of deployed that. I think I deployed it locally, but then ultimately I deployed that to. There was no concept of a cloud, but like there are some of those online services allow me to deploy, and the highest the peak concurrent user number was, I remember, was like 20 or 30. It's all my friends, my classmates. We had a lot of fun over there. Never experienced any issue. It definitely served the purpose. So this is like personally the earliest stage of server development. And then I graduated. I joined a company called Ubisoft, and we developed first-person shooter games. That's actually also a single server structure. In fact, this is the very, I would say, early stage server structure. It's really just there's no server. It's one of the client behaves as a server. And this is still popular use in a lot of first-person shooter games. Probably not today anymore, because a lot of servers, because anti-cheat, they wanted to make sure like the client do not have these also abilities to determine the server results. But at that age, this is actually very popular. Most of the first-person shooter games are doing that way. So you are just having, say, 10 players join this game session, and they just automatically elect one of the client to be the server, to behave as the server. Normally, we just use some algorithm, say, because of the connection, you are in the middle of all other players, you have the best kind of connection. So, or you have the best. I think at that time we were console games, so we don't. They all have the same computing power. But if it's PC games, you need to also determine the computing power, right? Because it takes a lot of your computing. So this is a first-person shooter game, multiplayer mode, single server structure, or we call that client-server model. Then I think I was in 2005, World of Warcraft launched, and I was a huge fan of that. And after that, I decided to pursue for a MMORPG opportunity. So I joined Tencent to develop an MMORPG game. At that time, we basically just used the server cluster I just mentioned to you, right? We have those game servers, but we also have those microservices. We have centralized data storage. We have gateway to send players to different game servers. So yeah, for this part, since you already know, I'm not going to give you too much of the descriptions. Then that's in early 2010. We call it so-called social game exploded. Like the early game, like Farmville, right? Some of you probably already you've heard about that. So, and we decided as a company at that time, we decided to start working on the social games. And what social games typically deal with is a massive number of users, which I'm going to give you a more detailed explanation later. And at that time, we use a tech stack called LAMP stack. Even today, a lot of internet companies, they are still building their server architecture under the LAMP stack. What is LAMP stack? Grab this image from internet. So it's basically Linux, means the operation system. The Apache web service means the web service. MySQL, the data storage service. And PHP, which is the language to write game logic or whatever the logics. So apparently you just can't just use this, right? This is a lot of problem with that. What we were doing at that time. So let me start from the very beginning. I'll just look upside down. So when the user traffic comes, it gets to the load balancer. And well, what is load balancer is basically it will use certain rules to distribute, to automatically distribute the traffic to all stateless or potentially stateful servers. It's very similar to the gateway I mentioned earlier, but gateway is normally non-scalable, but load balancer is scalable. Because the rules, all the components in the load balancer, they are stateless. When you talk about stateless, you means it's auto scalable, right? So you can easily just scale that. So it will take all the traffic and it will send them to we use Nginx web server, which is very similar to the Apache games web servers. But they are much faster. They're much simpler and faster. So we use that one. And then we forward you use a reverse proxy to forward the traffic to the actual game servers. We didn't use PHP to write game servers. We used Java because of all of our core game experience. PHP is way kind of too alien for us, so we use Java. But they serve the same purpose. So they just implement all the game logics, like all the user progressions, the things like that, right? Then we don't store the data directly to MySQL because MySQL is really a non-scalable server system. You could scale it, but every time you scale it, you need to take down the server and just migrate that to a higher end data. I mean, apparently today there are a lot of solutions to solve that, but at that time, that's literally non-scalable. And we also don't want all the traffic to just go directly to the data server, right? So to the database. So what do? We use a solution called memcached. I think very few companies are still using this, but this is extremely popular. You probably are familiar with Redis. So technically, it's very similar to Redis. So they are a key value-based sharding mechanism. They basically just take any of the data, you put it in a key value pair, and say use the user ID as a key, right? I want to store the user ID. and I send this user ID with all the user data as a value to the memcached cluster. And it basically will just do a quick hash of the user ID. It will map to one of the shard. So all of these are shards. So they basically just automatically just distributes the massive number of data to a number of physical storage systems. And you can easily scale them. Basically, just need to rebalance, which normally just to change just to add that and make a change to the hash or use those ring structure, just like what the contemporary sharding system used. And then but memcached does not have a persistence feature. So we have to use another service to persist the memcached user data to MySQL. Normally that's a standalone thread or standalone service that periodically persists the changed memcached data to the MySQL server, to a MySQL database. And then say if there is a server outage, the memcached or restart the memcached server cluster, and you can't find the user data over there, you basically just load the user data directly from MySQL and populate to the to memcached. So you kind of use this loop to keep the user data persisted. So yeah, this is the first time I experienced the contemporary server structure, and this kind of structure is still well used today in most of the social, casual, or mid-core games. Then I moved on to develop mobile games. Then, as I mentioned earlier, there are a lot of different genres of mobile games. There are casual game, mid-core game, multiplayer strategy, multiplayer role-playing. You just can't use one server architecture for all of them. So next, I'm going to give you some examples, basic for each of them. So first of all, the casual mid-core. And as I just mentioned, this is the first time I dealt with contemporary server architecture. And the key challenges of this was three of them. The first one is high DAU. Casual game, you attract a lot of players, right? Because the low friction, and we're normally talking about multi-million daily active users, even more. And this immediately present a challenge to the server capacity, which, as I mentioned earlier, that we want also to have the high scalability. Right? We want to make sure when the game goes viral, or there's a game event or much more traffic expected, you want the server to be able to quickly scale, and you just don't want to waste the server resource. Right? You don't want to scale the server to one extent, and the traffic just calms down, and you just waste all the computing power. So you want the server to be more kind of elastical, right? When you can scale that up, you can scale that down. So this is, we want a server to be very flexible. This is another key challenge we're dealing with these casual game servers. And third one is high availability. And this is actually a key challenge for all the servers, but this is uniquely important for casual game because casual player, they don't have a lot of patience. They have a lot of options. They are not like core gamers, right? For example, Genshin Impact, they always, sometimes they do those maintenance, right? A lot of users, they just wait, and even during that maintenance window, they will just do YouTube videos, they watch YouTube videos, just discuss. They have a lot of things to do. But for casual players, if there's a big downtime, they just most of them will just move on to another game, right? Because they have so many options. They don't have the kind kind of the liability to play your game. So we want to make sure like the server is highly available. So for most of those casual games, when we do the server update, we don't want to introduce a maintenance window. We want to just update that on the fly. The user does not have any feeling, and the server is already updated. And we just ask the user, okay, server is updated, please restart. Like this is normally how this works. So how do we deal with that? I actually drew a very simple graphic earlier, but this one is more sophisticated, which should give you a very good overview of that. So first of all, these are game clients, could be a tablet, could be a phone, could be a computer, whatever. Normally they use just a HTTP connection, the typical web request. And because they don't have like the demand for those real-time communication, right? Normally what they do is, okay, I click this tree, I wanted this tree to spawn something, I click this loot box, right? Things like that. So this one, I call that access layer. It's basically not really on the server side, but I want to mention, like, you can see CDN. This is the first time I mentioned CDN this presentation, but CDN plays a very important role. CDN Content Delivery Network. It's a very good way for you to access kind of static game data in the fastest way because of their CDN network. They have all the edge nodes, which is always close to you. So when you push some content to the CDN network, they will populate that to all the edge. Actually, they don't actively populate that. When the first time, say, a user from Singapore, let's say the source of this data stored in US, and the user from Singapore trying to access this source, in CDN it does is it will try to populate this to the edge nodes in Singapore, and then the user will then the data stored in the edge node will stay there. The next time another user from Singapore, when they try to pull the same data, they will just pull that directly from the edge node instead of from the source node, which is in US. So this is basically our CDN. They basically use to deliver all the game assets, right? Like graphics, like song, asset, right? All those things, animations, all those things. So sometimes we also, I'll mention later, but another part of that is network accelerator. Because if we are dealing with most of the games, they are using centralized data storage system, centralized server structure. They put that in one data center. Say I mentioned earlier in US, and it will host the player from all around the world. But sometimes, like, it takes a really kind of a weird route to reach the data, which results in a huge packet loss or big latency. What we deal with that, we use a network accelerator. They basically just find the most optimal way within your server nodes, to try to navigate the user request through the quickest route to the game server. And I put these two together. Sometimes this network accelerator is just using the CDN infrastructure. As I mentioned earlier, they have a lot of edge nodes. So they basically just utilize those edge nodes to build the connection between all the nodes and the game server. And then we'll provide the fastest connection to most of the players all around the world. So this is basically access layer. They're dealing with like the fastest way to download the game asset or static data, and the fastest way to send your dynamic data or the game request to the servers, the actual servers. So this is the access layer. So next one is the logic layer, which is actually your actual servers. And you can see the familiar face load balancer over here. And this is pretty much similar to what I mentioned earlier. So you have your game server, you have your utility server services, or should I say, and these load balancer will just send these requests to the game server, and they will persist them to the data layer. And I put all the kind of the mainstream data storage solutions here. Redis is not really a data storage solution, but they are really a data caching solution. Kind of they behave similarly to the Memcached because they are much faster. But we don't use, even they have the persistence kind of a function, but we don't use that to persist user data. We still normally use a typical kind of a transactional database like MySQL, which is mostly MySQL, and NoSQL, which is normally a key value storage or documented storage like MongoDB. They are highly scalable, but there are pros and cons of them. The pros, I mean, sometimes it could be both pros and cons because they don't have schema. So which means they are very flexible, but sometimes no schema presents a challenge for a structured data kind of like, for example, you want to do sorting, you want to those kind of data kind of a search. It could be more challenging than the typical MySQL or transactional data service. And for this, we normally what we do, I mentioned earlier, MySQL is not really scalable. What we really do is we use a DB proxy to kind of as a mid layer to bridge the connection between the MySQL and also allow us to scale the at least the reads of the data server, because they actually handle some of the caching abilities, and also allow us to use multiple tables and multiple even databases. They kind of behave a little bit similar to the gateway of database servers. So this is the typical structure of a casual or mid-core game servers. So next one is multiplayer strategy game. And a good example is Whiteout Survival. It's like we call it a 4X marching game. So you are battling with players in the kingdom or in different kingdoms. You're trying to kind of conquer more of the lands, and you send your troops over there trying to destroy their cities, things like that, right? So key challenges. First is the massive state synchronizations, because you basically dealing with a huge number of players. Each player have a lot of different game data, and you wanted to synchronize them across all servers. Across the game server. That basically means the kingdom, I would say. And this is actually a multiplication problem, right? When we say we have 100 player playing in the same server, and if we want to say every time one player does something, we want it to broadcast to all the servers, and which means if we'll do this, which means the server is actually broadcasting 10,000, because it's 100 multiplied by 100. The server is broadcasting 10,000 of state changes. And this is definitely the biggest issue that we need to deal with, right? We don't want it to just become a bottleneck. Another thing is like low latency, because a lot of PvP related, right? We don't want the player to just do one thing, they wait for a long time, or the other player already destroyed their cities, they didn't know that. And apparently there is a cross-server functionality. We want to make sure, like when we are dealing with those cross-kingdom battles, the player data could be properly migrated over there in no kind of data loss, without a data loss or any of the user experience interruptions. So how do we deal with that? This is a very simple diagram because I already I omitted like a lot of things already mentioned here. So it's just started from load balancer. Also, I omitted a lot of features I don't think it's relevant for this presentation. So typically what we do is we are behind load balancer, we also add a gateway. This may sound weird, but the reason of that is because we wanted to do this cross-server functionality. So, because as I mentioned earlier, load balancer just use simple rules to distribute the traffic. But we need more sophisticated rules. It's not just based on the player ID. It's based on where the player, which server the player belongs to, what the player is currently doing. For example, if the player is doing cross-server battle, the player data should be rerouted to another server instead of the player's home server, right? So that's why we need this gateway to deal with these more complicated requests, to distribute them to the proper game server. Another thing to solve the low latency, the latency issue, we use TCP, so the player will get response faster. We don't use those heartbeats to get that, but like the earlier the casual game. So I mentioned account server here. They basically means you will the player will have this is not very important, but basically for these type of game, normally one player they play different accounts, different roles. So we want to make sure like they always map to the right server. And then after that, we use the DB proxy to do the data storage or the data persistence. This is very similar. So the last one is the multiplayer role playing. And this is actually not very different from the MMORPG server I mentioned earlier. But why I put it here? First I want to let you know that like this is, like I mentioned, there are a few things for challenges. First is the real-time high-frequency player interactions, right? Like, this is like the most like performance demanding server. Like you want to make sure like it's like we normally call that the millisecond level like latency. I mentioned earlier, extremely low latency, because normally these games are action games, right? You do one thing, you want to immediately see result, and the other player they kind of want to expect all the move you are doing over there are kind of in synchronous with theirs. So, and this also introduced very complex game state synchronization because of the complex like environments, like terrain could be 3D, player actions, player abilities, all those kind of things. So these definitely posed a key challenge. And how do we deal with that? Like, because I mentioned the structure earlier, they could work. But if you just put that in a centralized server, how do players all around the world to enjoy, to kind of experience the same low latency experience, right? So this is how we introduce this cross-region server architecture. And basically, we still have the central service. They have all the key game logic. They have those data cache. They have the centralized storage, data storage persistence systems, but we have session servers all around the world. Just like CDN, they have edge nodes all around the world. We have session servers all around the world. So say if the central server is stored in US, a player from Europe, they try to access, they will be actually navigated to the server in Europe, say Frankfurt in Germany. And the session server will basically be the facade of the player. The player basically just playing in this server. All the play interactions are within this server. And then they will build a connection between these session servers and the central service. They will use the fastest like backbone network to achieve a close to real-time data exchange. But most of the time, these servers will just store user data. These will be just like a asynchronous data persistence to these, because ultimately we still want the data to be centralized. We don't want those distributed player data, which is really hard to manage. So same for all other servers. So ultimately player just to get like their latency could be just a matter of under 100 milliseconds. But if they connect to the US, that could be like 300 milliseconds. So that's already a huge improvement. So yeah, so let me see. Yeah, I think I wrapped this up in perfect timing. Bonus time is really just a Q&A. Okay, there we go. Okay, I'll start from the first one. In early days, games like MapleStory keep getting rollback maintenance. Does that mean there are duplicates of player data to your? Yes, that's a very good question. So we deal with a lot of these issues. How rollback happens? Normally, it's introduced by bugs. And why they have to do rollback? Because those bugs, they kind of corrupted player data. So let's say we have a bug introduced and accidentally multiplies the player currency by 100, right? And then this got persisted to the player data. And it's so hard, like sometimes it's so hard to just revert that because it's already part of the player property. So the simplest way is just to roll back that. And there are more like that. Sometimes, like I mentioned, the corrupted data could be even in the more worse way. Like you got data corrupted, and you couldn't even access to your player data, and there was no way to fix that. So you had to roll back that to the previous state. So even today, we keep those user data backed up in a very frequent state. I mean, in a very frequent cycle. Some of the data storage systems they have, like for example, MySQL, they have Bing log. You could use that to kind of roll back data. But yeah, this is basically. Also, as you mentioned, duplicates could be also a way. Like for example, player figure out a way to do dupe, which is duplicate some of the game item, and it's really hard for you to just remove all of them. So the easiest way is just roll back, like fix that first and roll back to the clean state. All right, hope that answers your question. Second question, if your server is supposed to handle so many players, how do you test it when the game is not out yet? Very good question. We do stress test. So how do we do stress test? A lot of ways of doing that. First of all, you just spawn bots. You design game bots. Bots is already the second phase. The first phase is we just do the interface test. Yeah, we just initiate a lot of requests, sending that to the server and see if the server could handle that. But this is normally not reflecting to the actual scenario, because players are not just doing that all together in the same kind of protocol or same packet, right? They have their own player behaviors. That's why we introduced bots. We kind of spawn a huge number of bots and we simulate the actual player behavior. There are multiple ways of doing that. First, you could record player behavior. So you record all the actual game traffic sent from QA or tester, and you kind of replicate that to multiple. You kind of integrate that into the bot, and you just do that, making those bot kind of like the real user. The other way is you give bots some kind of you write some script, right, to make the bots to behave like a real person. And the third way is definitely utilize some AI technologies to make that bot kind of to behave more like the real person. But I don't think third option is widely used in stress tests. This is way too costly. So yeah, but that's something like we could do, but not something like very cost effective. Yeah, so stress test is the way. Stress test is not just for testing the server loads, but also testing the server behavior in different scenarios. For example, if you want to just increase the server, so if you want to scale the server under pressure, you wanted to do that in stress test, right? You because when you scale a server, sometimes there could be some bugs or something you didn't considered. So you say you add one node to that, but it's not properly registered to the cluster, so it's not really taking any traffic. Or you remove one node, it could just destroy the entire server cluster. So we want to also stress test these kind of server situations. All right, you guys all question was really good. So next question. Thank you. Sorry. How does your company or you set benchmark of global server architecture within the game industry? I don't think we set a benchmark. We always try to follow best practices. I could tell you how do we internally audit the server architecture. So we do tech review within the company and at different phases. We have typically 2 to 3 different gate reviews, and then before this game launches, we have another kind of a checklist review. So at different stage, we want to evaluate the server architecture in a different way. Early stage, like gate review 1, we want to review the overall architecture. So we want the game team to submit a tech design document, including the server diagram or the server architecture diagram. We want to make sure like every nodes or every part makes sense, and what kind of the third-party services or third-party tech stack they use, and how do they work with each other. If there's any kind of obvious issues, for example, we don't want to have single point failure, which means like when there's one node of the server is having issue, then your entire server cluster just got busted. We don't want that. So we kind of review the server architecture to make sure they handle different scenario or situations well. Then before the game launch, we will want to do that. We have a checklist. They basically goes through all the best practices and also the must-do things. And then we review them, and then we'll have our QA team to do stress tests for them. And we normally don't want the game development team to do stress testing by themselves because it could be biased, right? They always know what's the server design, so they basically just tested what they think should be a problem, but sometimes there are more than that. So we have a third party, which is our central QA team, to stress test the server for them. And then there are definitely standards. We also compare some of the metrics with our the games of similar genre, and within our company, we can easily benchmark that. But there are sometimes their competitors are outside of our company. How do we do that with that? Normally we just use some of the client metrics. For example, how long you connect to the server, how long to launch your first session. We also use a technique called weak network test. So we simulate a weak network environment. Say we added a packet loss, or we increase the latency artificially, and we see how this can behave in this environment to simulate those real world environment. And then we compare nodes with the competitors. We normally want to make sure under different circumstances, we outperform the competitor. So this is how we set the benchmark. Right? So many questions. I just try to, I don't know how much time we have. We just try to do that as fast as possible. So next question, for large MMORPG game, how to set or expect user loads to prevent server from crashing? Yes, we normally have a pretty good idea of how many users each server could host. And this is how we normally do stress tests. And normally for these MMORPG games, there is a pretty much golden standard of how many concurrent users you should host on a single server. Because if there are too many users, then it's actually doesn't make a lot of sense, right? So we normally want to make sure like users, the environment is competitive and social enough. So normally a few thousand concurrent users is really a good number for a MMORPG game. So normally when we design these MMORPG server, even for those like multiplayer strategy server or 4X server or SLG server, right? So we normally just allow the server to take around like 50,000 users, like registered users. And this normally contributes to a few thousand concurrent users. And this is pretty much, I would say, a golden industry standard. And we just want to make sure these servers could handle that loads. I mean, we definitely don't barely handle that loads, right? We just want to make sure like the server could handle double, triple that kind of load. And then if the server is full, then we, for all the new users, we will try to open a new server. Apparently we're running out of time, but are we? Actually, I don't know.
No, sorry, there's still a few more questions.
Okay, cool. So yeah, good question. For the next one, how does server deal with cross-platform? For example, PC and console playing on the same server. Actually, for server, it's not that complicated, believe it or not. It's regardless different client, you are always using the same protocol connecting to the server. So from the server end, we actually don't really care where you are coming from. This is actually a bigger problem for the user experience. So for example, when you're playing Genshin Impact on phone and on PC or on PlayStation, you have different control pattern, right? You want to make sure like is yeah, you're yeah, I don't see much on the print. Yeah, so actually I would say most of the casual game are supporting cross device, cross platform. Yes, some of the like first-person shooter game, they do that just because the user experience can hardly match across platforms. Like the phone user definitely have disadvantage over console players, right? Console player normally will have disadvantage over a PC player because mouse and keyboard definitely does the best in first-person shooter. I know some first-person player, they do console really well, but most player, the mouse and keyboard is the best. So I think this is typically the primary reason why those data are segregated, not the server side consideration. Yeah, but good question. So next question, how does servers deal with, so this is the first. Next question, do you have any learning resources for game server architecture? Believe or not, no. I no. It doesn't mean there are no learning resources that you can find. But for myself, I remember when I started to develop social game, there were hardly any books that telling about those social, because they were so fast, right? So most of the time I'm trying to just read on some published papers, but actually for these server architecture there are very few papers. So for this case, there are presentations. I remember when I started working on the social game, I think I watched a GDC presentation by Zynga. That was in, pretty sure it was 2010. I think it's called like a multiplayer server, sorry, massive server, whatever. So they basically described that improvement of LAMP stack in that kind of server architecture. And then I remember when I was working on a lockstep server structure. I didn't mention that earlier. It's like very specific. That means like you are dealing with those extremely low latency environment. I also checked one of the GDC session by Blizzard. I think the Overwatch team, they have a very good presentation about how they use prediction and rollback in a server architecture. This is about the session server. It's not really the massive server structure. This is about specific game session and all the users connect to that. How do you synchronize the user data? And they have a very good presentation about that. And then this is basically my way of getting understanding the latest technology, and then trying to do some experiments, crowding a lot of internet publishers and articles. A lot of people are discussing on the internet, taking some of my past experience, trying to put them together. But I'm pretty sure there are good books that give you a very good overview. But unfortunately, I couldn't recommend some to you earlier at this point. The next question, with VR game, how would you go about tackling the architecture? We also develop VR game and AR games, but I don't think VR game, they are the challenge on the server side. They're mostly on the, I personally really think it's game design. How do you design a game that immersive in a VR environment? And the biggest problem about VR is you need to put that on. It's actually not easy for the user. You need something to retain the user. A lot of VR game, their issue is like the user will try this. It's a fresh experience, it's fun, so cool. Blade Beats, right? The Blade Beats, yeah. Like I play that, then actually Blade Beats is a good example. It's like I actually most of the time I play VR game. I play Beats. I think not Blade Beats. Whatever. I think it's Blade Beats. I play that, but for a lot of other VR game, I play that once. Oh, it's cool, but there's no motivation to drive me to play that second time. I think the challenge is really over there, not the server architecture. They are very similar. So next one, how to make server costs cheaper. First of all, this is always the last thing I would worry about. Just to be very frank, transparent with you. As a CTO, I worry the least about the server cost, ironically. Because your top priority for developing a game is always growth. You want to support the game to grow first. Like things like stability, scalability, right? Those things are what you really need to focus. And then when the game takes off, then you start to worry about the server cost. But this doesn't mean server cost is not important. There are a lot of ways to optimize server costs. I can't just give you, I mentioned earlier, like how do we improve the server performance, right? This is a very effective way to reduce server costs. And how do you make sure all your resources are properly utilized, right? You don't want to design a very complicated server architecture, like a lot of different modules, and some of them are not really taking any traffic. And why you spawn some of the server resources over there, it's just a waste of this resource. This is like how to optimize the server architecture is a very good way to reduce server cost. And apparently there are some other ways, like really just working with the cloud service. Nowadays we deploy all our services in the cloud services. For example, in Amazon Web Service, you can use reserved instances, right? Which is really highly discounted server. So you just reserve the server instance for say 3 years, and they could be like I think 1/3 of the cost of a typical like on-demand services. So things like that, and there are a lot of ways of doing that. So yeah, there are a lot of ways to reduce server costs. Like I said, this is not my top priority for most of the cases. All right, next question, how do you maintain determinism across different hardware and architecture? Very good question. This is like the lockstep issue I mentioned earlier. So for example, if you just calculate the different, because different architecture, for float, right? They could be resulting in completely different results when you're doing some float calculation. And randomization is also an issue. But how do we do that? We use pseudo randomization. We basically design a determinism way to randomize numbers instead of just letting the operation system to randomize that for us. The other thing, float, we avoid using float. We basically convert all calculation into integers and or like a float system, a data system we implement by ourselves. So there are a lot of ways and to handle these, but yeah, that's a good question. But they are very specific to what you really need. Okay, last question. What would the server architecture be like for a first-person multiplayer shooter like Counter-Strike or Call of Duty? First of all, take a look at Unreal multiplayer structure. They have a very good kind of documentation about that. All right, hopefully this answers the previous question, what kind of things I could recommend study resources. Unreal documentation is really good. Try to create a multiplayer game in Unreal, understanding how the networking system, multiplayer system, because Unreal uses a client server-based system, how everything, how the replication works, how it optimizes on the different situations. And this is actually, yeah, we don't have a lot of time today. I mean, if I really tell you how do we do that to solve it, probably take another at least half hour. But Unreal, the documentation, multiplayer documentation, should be the way to go. Yeah, cool. Thank you. It's really good question. I actually did some presentation somewhere else. You guys, the quality of the question, you guys are definitely the best. You guys are definitely well prepared. And thanks for staying an hour and 20 minutes with me. And I hope this is helpful for you.